We'll talk about online optimization and learning under long-term convex constraints and objectives.
Thanks, Shipra. The plan is to talk about 3 papers that are joint with Shipra Agrawal and briefly mention one other paper that's joint with Shipra and Li Hong. So these papers address different problems, but they are very closely related. And I will mostly focus on the definition and the algorithms and techniques used, which means I will not have much time for proofs, which is probably not a bad idea considering this is the last talk of the day. And also I must skim on related literature, hopefully that's pardonable too. The overarching theme of these problems and these papers is, so these are online, of course, there's a learning component, plus there are constraints on the sum of outcomes over the entire time period. And similarly, the objective is some function of the sum of outcomes. So that's the common theme here. I'm going to start with the online packing problem. Instance of this problem is a packing LP of this form. You want to maximize this b.x subject to the constraint ax less than or equal to c and x bigger than 0, plus some local constraints. The matrix A, the vector B and C are all non-negative. The columns of this matrix arrive online. Many columns may come at the same time. So each column corresponds to a decision variable, and you need to set all the decision variables at the time they arrive, and you cannot change them after that. Okay. There are also some local constraints. So for instance, the local constraints could look like, the sum of all the decision variables that arrive at the same time should sum up to 1, it should be integral, and so on. How do we measure the performance? It's a usual competitive ratio. You look at the ratio of algorithm to optimum. Algorithm is your reward, and optimum is the reward on hindsight. Here's an example of this problem. Ad allocation. So an ad opportunity, or it's also called an impression, arrives online and can be assigned to many advertisers. Each assignment generates a different value. And there are global constraints. So each advertiser has a capacity, which is the total number of impressions assigned to him shouldn't be more than some given number. Okay, you want to maximize the total value generated by the assignment. So this is an instance of the packing problem. The decision variables corresponding to a single impression, these are the ones that come online at a time, and you need to set these. So they must sum up to 1, and they must all, they must be integral. So you need to assign the impression to one agent. There are many other examples of this in network routing, crowdsourcing, and more general problems in ad allocation with multiple ads on a page and so on. We'll consider stochastic models. So one stochastic model is a random permutation model. So in this model, an adversary picks the entire instance and also the groupings of the columns of A and the local constraints and so on. But after he does this, nature permutes the order in which these arrive. So it's a random permutation, and the entities arrive in a random order. So the optimum is independent of this order, but the algorithm depends on it. So we look at the expectation of the algorithm over this order. Suppose we make additional assumptions. Suppose each entry of a row of this matrix is a factor b smaller than the corresponding entry in the in C. And the other assumption is that the algorithm knows t. So how many time steps are there? So under these assumptions, the result, the state of the art is something like this. You get a competitive ratio of 1 minus epsilon as long as this b is bigger than log n by epsilon squared. Okay, so as b grows larger and larger, the competitive ratio tends to 1. And the n is the number of rows of A, and C prime is some universal constant. Okay, so these are the kind of results that are known for this. We will consider a closely related model, which is called the IID model. Here, and this is the model to think of for the rest of this talk. So here there is a probability distribution supported over what? Over this set of columns that arrive together, right? The entity that arrives at one time step. And these could be possibly uncountable. And in every time step, I sample one entity from this and present to the algorithm. So this is a set of columns of A, or the decision variables that need to be set, and some local constraints, and so on, all that jazz. The algorithm doesn't know this distribution, but it knows T. Okay. And the ID model, it's easy to see that it's a distribution over random permutation instances. So any algorithm that works for the random permutation, for instance, algorithm that gives this, also works in ID. And for all interesting cases, I know the converse is also true, but that's not a theorem. So these are very closely related. And so here's my related work. There's a whole line of work that eventually got something like this, starting with my paper with Tom Hayes, then Feldman, Hensinger, Korolla, Mirokni, Stein, Agarwal, Wang and Ye, my paper with Kamal Jain, Sivan Wilkins, Kassalem et al., Gupta, Molinaro, and I'm missing some others. Okay. So that's my related work. Okay. So here's a generalization of this problem, which we call online stochastic convex programming, and this generalization is in quotes. Again, it's online T time steps. Now in one time step, you see some set ST, subset of 0 1 to the n, so some set, okay, and this is presented to you, and you have to pick a vector in this set. Okay, you pick VT, and we repeat this. Okay, some other set is given to you, you pick a vector. What is your goal? Your goal is to maximize some function, this is a concave function, of the average of all the vectors that you see. And there is also a constraint, which is again the average of all the vectors that you see must be in some set S. So think of this as a soft constraint versus the hard constraint that was in online packing. And these F and S are given ahead of time. So this is not what you are learning. Now the packing is a special case. How is that? So what is ST? So now think of when you get a set of decision variables, all possible valid setting of decision variables, and then look at the corresponding row sums that result because of this, and the reward that results because of this. This is your vector. So all such possible vectors is the set ST, and so your objective is just the one coordinate that corresponds to the reward, and the constraints are just box constraints, that the average must be within this the C by T. So the packing is a special case. But here when we look at this problem, we look at regret rather than competitive ratio. So the regret is the additive, so just a difference between opt minus algorithm. And we also need a regret in the constraint, which is just the distance from this set. So this is a by criteria. Okay, so you can see it's very closely related to the packing problem, but it's not quite a generalization because of two things. One is we look at regret instead of competitive ratio. The other one is this hard versus soft constraints. But nonetheless, the algorithm that we designed for this also work for that. It's easy to specialize this and make sure the constraints are always met and convert the regret to competitive ratio and so on. Okay, again, why do this? So going back to add allocation, there are many instances of this kind of non-packing constraints. One example is diversity constraint. So an advertiser has an ideal mixture of demographics in mind, and he may not be able to get this exact mixture, but you can place a constraint that the actual mixture that he gets should not be too far from the ideal mixture. Okay. You can also have nonlinear objective. For instance, if you allocate someone an advertiser much fewer impressions than his capacity, then the loss is not just a missed opportunity, but also there is some long-term impact on such an advertiser, so the loss is some kind of a nonlinear function. And you can have other things such as, you have not just the revenue, you have some notion of relevance, clicks, and all kinds of things, and you might want to maximize some concave function of these things. And similar applications are also, arise in crowdsourcing and so on. Okay, so I want to present an algorithm for the more general problem, and I'm going to use online convex optimization as a black box. Okay. So let me do a quick review for what is online convex optimization is. Again, this is an online problem, t time steps. Here what happens is the algorithm picks some vector theta in some domain delta, and after it picks this, it sees a convex loss function which is called gt. Okay, and then you repeat this many times. Now what is the loss of the algorithm? It's just the gt of theta t, and the optimum is the optimum static theta that minimizes the loss. And the regret is algorithm, the difference between algorithm and optimum, and all you keep in mind is that regret scales as square root t. There are other parameters, just forget about that. Okay, so now I want to use this black box for online convex optimization to design an algorithm for this online stochastic convex programming, right? And in fact, think of the case where there is no constraint. There is only this objective f. We're trying to maximize f of the average of all the vectors that you picked. Okay, so how do you do that? So the first step is to initialize this online convex optimization with a domain equal to the ball of radius L around the origin. Okay. Now what you do when in time step t, let theta t be whatever the online convex optimization is playing. Now you get the set st and you have to pick a vt. What you do, you just maximize minus the linear function given by theta t, which is rather minus theta t. Okay, and you just play that vector. So this you have played, you pick this vector from this set. Now you have to run the online convex optimization, the black box. So you need to define the gt, the loss for this, and you define the loss this way. It's f star of theta minus theta dot vt. So what is this f star? This f star is a Fenchel conjugate. Okay, so it's defined this way. So don't bother if it all looks mysterious. What is happening geometrically? So look at this function f star of theta minus theta dot vt. Here we thought of this as a function of theta for a fixed vt. Okay, you can switch this. You can think of this as a function of v for a fixed theta. Now what is this? This is a linear function of v, right? It's just theta dot v, and this is a linear function that is tangent to f and has slope minus theta. So what we are doing is linearizing f by taking tangent with a given slope. So that's what we are doing, and we are just maximizing greedily this linear function. And every time step we are picking a different tangent, and we are specifying the tangent by specifying the slope of the tangent. Yes.
So what you are saying is, as long as this tangent maximizing linear function will give you exactly the result of maximizing the convex function.
No, I'm saying that what the algorithm is doing is that every time it's picking a tangent to the function, and it's just greedily picking the vector that maximizes this tangent. And then just by staring at it, this gives you an interpretation for the f star. This must be the y-intercept. This must be the value L theta at 0, right? So, this is a geometric. This is the way I think of Fenchel dual. It's the y-intercept of the tangent with a given slope. Okay, and you can also think of this as a primal dual. Thetas are like dual variables, and what the OCO is doing is searching over the dual space. Okay. So why does this work? I said no proofs, but okay, this is the only slide that has proofs, and I'm going to give you only the very high level idea. It's very interesting. What happens is there's a switch. The value of the algorithm for the OSCP is exactly equal to the opt for OCO, and opt for OSCP is upper bounded by the algorithm for OCO. So this difference is smaller than this difference, which was a regret for OCO. Okay, so it's switch. I don't know why it's happening, but this is what is happening, right? So the first thing is actually easy to see. So what is the value of the algorithm? It's the value of the function f at the average. And using differential duality, I can write it like this. This is the minimum overall theta, f star of theta minus theta times this average. And if you just go back and see the way we defined this GTs, this is just the average of all the GTs. This is how we defined this. So all the GTs have the same convex component. The convex component is the same, f star of theta. Only the linear component is changing. Okay, so when you average them, the convex component comes out and the linear component just averages out, right? So, but this is the optimum. So it's a minimum theta, right? So the optimum for OCO is exactly our algorithm. Okay. Now this thing is a little more complicated, and this thing holds actually only in expectation. The opt for our algorithm is less than the algorithm, what the algorithm gets for OCO, and this is where we use the IID assumption or the random permutation assumption. And so to get some idea of what's happening, so if you look at the algorithm, the OCO algorithm, what it is getting, it's getting this GT of theta t in the average of those. And we can switch this, right? So as I said, I can think of this as a function of Vt at this L theta of t of Vt, right? So now this is a linear function of Vt. And how was Vt chosen? Vt was chosen to maximize this L theta t, right? That was the definition of Vt. So I can plug in any other, let's say Vt star, this is the intended, what the optimum chose. I can plug in that, and that will only be smaller. So this is actually pointwise. But now when you take the expectation and then you do some more calculation, this is at most optimum, because of this uses concavity of f and other things. So I'm not going to go through this sequence of inequalities. But this is believable, right? So this switch is happening, and that's why we get the regret. Our regret is bounded by regret of OCO, and what we get is essentially something like this. We get 1 by square root t regret. L is the Lipschitz constant of the function f, and the c, it depends on which norm you choose. If you choose measure the distance in L2 norm, we get n log n. If you measure it in L infinity norm, we get log n. And so that's why for the packing problem we can use L infinity norm, and that's why we get this 1 minus epsilon computator ratio as long as the budget is log n by epsilon squared. So that corresponds to this square root log n by t type form. Okay, so the algorithm was very simple. The proof is also not so complicated. The problem seemed.
Where does the distance come? The norm?
So the norm comes, depends on how you measure L with respect to what. With respect to what norm, basically. And also this, the OCO, this is coming from what the regret you can get for OCO. That depends on your domain and so on. Like we define the domain of theta to be the ball, so whether it's the L1 ball or the L infinity ball and so on. If it turns out that it's the ball in the dual norm, so if you use L infinity, that's like a simplex, so and then you get log n. In fact, if f has some more structure, there is an even simpler algorithm that gets even better regret. It gets log t by t regret, and this is called the Frank-Wolf algorithm. And this f has to be smooth. I'm not going to define what smooth is, and the algorithm is very simple. Now you just use, instead of saying what the slope is and trying to find the tangent at the slope, you just find the tangent at the current average at where you are. Okay, this current average, just look at the tangent to f at that point, and then just use that to optimize over your set ST. And that's it, everything is as before, and you get log t by t regret. And again, the proof is not that complicated, but this requires a smoothness assumption, and sometimes you can use a smoothing operator to convert non-smooth functions into smooth functions. So these are standard things. Okay. So yeah.
just ask about the previous thing. So you showed that you switch between ALG and opt, but typically you say that ALG is not much worse than opt, but it could, in this regret thing, ALG can be much better than opt. So in sense, it cannot happen, and then we switch, you lose this thing. I mean, it cannot happen that ALG is much better than opt, because opt is a fixed thing, and you switch every time.
So for regret,
Yes.
yeah.
And here you show that you switch between.
Yeah, in this case it cannot be, yeah.
So you have to prove it.
Yeah, so this implies it, I guess.
Yeah, because typically, I mean, you could get much better than opt, because opt is fixed and algorithm is not.
Yes. Yeah, in this case it is showing that you cannot get much better. But this is a special case of the regret minimization problem, right?
No, the second inequality, why is it true? So their opt is
This one. So it's a proof, so I don't want to go through the proof in detail.
I guess this question might be that the actual opt of the OCO versus like comparing to single best theta, is that?
So also this is in expectation. So for this instance of OCO, what you're saying cannot happen. In expectation. So the second thing is in expectation. So maybe for some instance it can happen, but in expectation it cannot happen. Because we defined the convex functions in a very specific way. So that's a good observation though. Okay, so now, this is a algorithm when you only had the reward, right? So what happens when you have reward and constraint together? So here, what we need to do is we need to combine the reward and the constraint using some parameter which we call z, and z is roughly the rate of change of optimum as I relax the constraint. Okay, something like that. And if you know z, then what you do is you can run a separate instance for the reward, separate for the constraint, because constraint also you can just think of as a reward. It's just the distance from the set. It's a negative of the distance from the set. That's a concave function. You run two separate instances. You can use Frank-Wolf for one and OCO for other and whatnot. And you just combine the two. You get a linear function from here. You get a linear function from here. Just combine the two linearly using this multiplier z as a multiplier. And if z satisfies something like this, then everything works. Okay. But you don't know z, so how do you estimate it? What do you do? So you estimate it. And in particular for the packing problem, estimating z turns out to be equivalent to estimating opt. So you can just look at the first few samples and estimate opt from here. And you only need to solve a single LP for this. And previously, all algorithms before this for solving the online packing problem, they needed to solve LPs multiple times because they needed very good approximation for opt. So they needed a 1 minus epsilon approximation to opt, because the error went into ALG. But here the error goes into the second order term, it goes into regret. So we just need a constant factor approximation to opt. So we can do it with much fewer samples and just solving it once. Okay, so the summary for this part is we gave a very simple algorithm for this problem, very general problem, using this OCO as a black box. And essentially the same algorithm works for online packing. And it works, so if you look at the analysis, it also gives you the difference between random permutation and IID, although I didn't touch upon that. You can also use the Frank-Wolf algorithm if F has more structure. And this also has connections to Blackwell approachability, so if I have time, I'll touch upon that. And just one thing I want to say is, Tim talked about beyond worst case, and I think this is a very good application of beyond worst case. So this was motivated by practical applications and has a rich theory, and these algorithms are actually being used by almost all the companies that run ads. So this was exactly in the framework that Tim said. We are doing as well as an algorithm that's tuned for the particular distribution, but without knowing the distribution. We're doing worst case over family of distribution. Okay, so now the second problem. So this problem is called bandits with concave rewards and convex objectives. So this is very similar to the online, the stochastic convex programming problem. So, but the difference is, you don't see the set from which you are choosing the vector. So the outcome is still a vector, but you don't see the set. What you choose is an arm, and for each arm there is some distribution over vectors. And so if you pick an arm, then you get a vector sampled from this distribution. Okay, so that's the difference between how the vector is chosen. So compared to the OSCP, in OSCP ST can be arbitrary in each time step. But here the choices are persistent. So it's the same choice set that you have, versus where the choice set is different in each time step. But there, the ST can be seen ahead of time. You know what you're going to get. But here, you make a choice, but the outcome is stochastic. Okay, and then there are many examples. I'm going to skip this. So what's algorithm? Again, you use the same framework. So you linearize the function using OCO or Frank-Wolf. But now you don't have the set. So what do you optimize over? But you have arms, right? So you want to optimize over arms, but you don't know what you're going to get. So what you need to do is you need to build confidence intervals. And you use the most optimistic choice within the confidence intervals to pick the best arm that maximizes this linear function. Okay? And then again, similarly, you can combine, if you have F and S, you run separate instances for each, and then you can combine. And here in this case, you don't need any Z or anything, because the choices are persistent, so you get a sense of the scale of the objective and the constraint. You can just solve a simple LP and use that, or you can even use something even simpler, so that the whole combination aspect doesn't come here. So it's easy to combine. Okay, and then again we get result something like 1 over square root t. So now we have seen these two different problems. So one in which you see the information ahead of time, you see what choices you're making ahead of time. One where this is a stochastic outcome. And there's a common generalization of these two. It's called the linear contextual bandits with blah, 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 blah. Okay? So it has common aspects from both. So one aspect from OSCP is you see the information before making a choice. You see something. Okay? But then the outcome is still stochastic. So how is that? So here again there are k arms. Now for each arm you see a context vector, which is in 0 1 to the n, and these context vectors are drawn IID. But the outcome vector is not the same as context vector. What we know is the outcome vector is some linear transformation of the context vector plus some noise, some zero mean noise. Okay, so that's the stochastic part. Now how is this a generalization? For OSCP you just make the linear transformation be identity. Okay, and the distribution is actually, the noise is 0. And each vector in your set ST is an arm, so to speak. Right? So the context is the outcome. That was the OSCP problem. Okay. Now what about the bandit problem? Here the context is trivial. It's not giving you any information. So you just have the arms, and then the outcome vectors are some IID draws from some distribution we don't know. Okay, so both of these are special cases of this more general problem. Now here the main goal is to get a regret that's independent of the number of arms. So it can depend on the dimension. There are two dimensions, the dimension of the context and the dimension of the outcome. But it should be independent of the how many arms are there. So because typically we want to apply this where the number of arms is very large. Okay. And so this we can solve only for the special cases of packing and when there's only the objective function f. I'll say later on why this is so. And we get again kind of root t types regret, but we need additional assumption here. We need for instance the budgets be at least n times t to the 3/4, whereas earlier we only needed n square root t. So this problem is more than the sum of its parts. Because we're not able to match the bounds we get for the special cases. So this is something more going on. So what's the main idea here? So the main thing is we need to estimate this linear transformation W, the matrix. Okay? But we don't observe samples from W. We observe this W applied to some vector plus some noise, right? And there's a way to kind of estimate W from such observations, and this use confidence ellipsoids. So now we build confidence ellipsoids, and now for each arm we pick the most optimistic estimate within the corresponding confidence ellipsoid with respect to the linear function that we are optimizing. Okay, so that's the main idea, and we can still do this. Everything works out. Where things start failing is, or start getting more difficult, is in estimating opt. So in both OSCP, for instance, you had full information. You know exactly what came, so you could estimate opt from the samples. Or if you had some kind of bandit, you could do this pure exploration and estimate opt, but that gives you dependence on the number of arms k. So opt requires you to kind of estimate what happens no matter what action you picked in the past. But how do you do this without depending on k? And we give a way to do this. The way we do it is we use the first few rounds for kind of pure exploration. And how should you do pure exploration? What you should do is you should pick the arm whose context vector is closest to the longest axis of the ellipsoid, because this is the direction of most uncertainty. And if you pick this arm, then that shrinks the ellipsoid in the optimum fashion. And using this, we show that we can estimate opt for the packing case, but we don't know how to estimate this z parameter in the more general case, in the more general convex case. And this is where we don't know how to. This is the reason why these algorithms don't work more generally. So if you give me z, everything works, but we don't know how to estimate z. So that's the main difficulty. And these are okay. So this is related to black hole approachability. And I'm out of time, so I'll have to skip the last part, the contextual bandits, which is a little unrelated. Okay, so we saw three problems that involved this learning plus long-term constraints, and the main idea was to linearize these convex functions, concave functions, and the constraints, and just do greedily pick the one that maximizes the linear function. But how do you pick these tangents? So you can either use some kind of regret minimization algorithms, or with more structure, you can use a Frank-Wolf algorithm to pick these linearizers. And when you have bandit, you need to estimate confidence intervals or ellipsoids, and you also need to estimate some parameter z or opt to combine objective and constraints if you have both. So some open problems are, so in the linear contextual case, we don't know how to estimate the z. So we don't know how to extend the algorithm to the most general setting. And the same thing happens with the other problem that I didn't mention. And a slightly different track of problems is when I make a choice that consumes some resource, but it doesn't consume it forever. So here, think of packing problems, right? So you made some decisions that consumed some resources, and you have some capacity that's done forever. But suppose you make some choices that consume some resource for a while. Like think of servers that are busy for a while, that are doing a job, and then the job is done, and then the server becomes empty again. And you can think of similar problems in that setting, and I think that's a very interesting line of work. So, thanks.
Take a few questions. Okay, there are no questions. So let's thank the speaker. And